Hello, welcome to my talk on elementary potential flows. This is the second part of the talk on the building stones for potential flows. In here, we'll talk about the flows from sources and sinks. In this talk, we will see the velocity potential functions and features for 2D source or sink. And then we will see in a better expression of the potential function in polar coordinate. And we will see the strength of the source. Then we will look at the stream function in 2D polar coordinate. Then we will see the equipotential lines and stream lines for source or sink. And then we will have an examination on the potential function for a 3D source. In here, we consider a source with a flow rate Q at the origin, see here. And the fluid potential function would be given as phi as this. If the source is a 3D source, then the potential function for the 3D source would be given as this. Here we can see at the origin of the coordinate, where x and y are both 0, the potential function phi would be singular. This means a source is a singularity. This is the same for the 3D source. At the origin of the coordinate, x, y, and z are all 0, so this would be singular. From the potential function, we can calculate the corresponding velocity components u and v, given as this and this. Because we have the velocity expressions u and v, so we can calculate the partial differentiation of the velocity u with regard to x, which would be given as this. And the velocity component v, its partial differentiation with regard to y is given as this. So if we put all these two terms together, and we can see this term and this term together, we have this term. And this term and this term together, we have this. And obviously, we can see the result of the expression would be 0. This means the flow from a source is an incompressible flow, because the expression is 0 means the continuity equation for incompressible flow. And we can easily to check the Laplace equation, it is satisfied. This is understandable because the Laplace equation is derived from the incompressible continuity equation. Based on the velocity components u and v, we can also calculate the partial differentiation u with regard to y. It is given as this, and the velocity component v, its partial differentiation with regard to x is given as this. So if we put this term minus this term, and you can see this are same, so the expression would be 0. This corresponds to expression, the core of the velocity vector is 0 in 2D flow. Therefore, the flow from a source is an irrotational flow. For the 2D source, the potential function is better expressed in the polar coordinates, see here. So the potential function in polar coordinate would be given as phi equaling to this. Here, in the polar coordinate, we use r, the distance from origin to the point, and the theta, the azimuth angle from x-axis, and the relation between the polar coordinate and the Cartesian coordinate x, y are given as this. And the velocity component, we calculate ur, given as this. This is the radial velocity, and the velocity component u theta is the tangential velocity. So we can see here, for the source flow, the tangential velocity component is identically 0. So in the polar coordinate at the origin, where r equaling to 0, the potential and the radial velocity ur would be infinite. That means r equaling to 0 is a singularity. In practical applications, it is the singularity which could lead to some beautiful mathematical expressions. When we desingularize the singularities, we will see this when my talk is moving forward. Now in here, we can make a circle of a radius r around the source, and the center would be at the origin of the polar coordinate. See this dashed line. On the circle, the velocity component ur would be calculated as this. There's no tangential velocity component u theta because it is 0. So the flow rate passes through the circle is calculated as q prime as this, and we can substitute the velocity ur into the integral. We can see r would disappear, and we can see the flow rate pass through the circle is equal to the distance of the source q. Because of the flow rate emitted from the source is a constant q. This is why we call q as the source strength. Now in this slide, we will build the equations for solving the stream function. Since we already know from the potential function, we have the velocity component ur and u theta. And accordingly, if we have the stream function psi, then we can use the velocity component to build the equation for the partial differential equation for psi, given as this and this. So from the first equation, we can see the partial differentiation of psi with regard to theta is given as this. So we can integrate psi would be given as this. If r is the function only dependent on r, and apply this equation for psi function here, we can see fr would be 0 or a constant. So if we assume psi equaling to 0 when theta is 0, then we have the stream function psi given as this. Since we have already obtained the velocity potential function and the stream function, so we can draw the stream lines and the equipotential lines. For equipotential lines, based on the potential function phi given as this, thus we can see when r taken different values, this means the potential would be a different value. Thus, the dashed circles are the equipotential lines. And for the stream lines, it is dependent on the stream function. The expression for the stream function is given as this. Therefore, when theta taking a different value, so we have the radial lines, the arrows. So the arrows are the streamlines. For practical applications, 3D source would be more useful. Thus, in here, we will have a look at the 3D potential function for a source. It is better if we can employ the spheric coordinate, see here. And here, we can see the transform relation between the Cartesian coordinate x, y, and z, and the spheric coordinate r, theta, and psi, given as this. Then in the spheric coordinate, the potential function would be simply given as this. The velocity component would be calculated as this. The radial velocity ur given as this. And the polar velocity u theta is 0. And the azimuth velocity u psi is 0, 2. So in this example, when r equaling to 0, that is x, y, and z are all 0, then we can see the potential function and the radial velocity would be singular. Thus, r equaling to 0 is a singularity. Since we already know the potential function and the velocity component in the spheric coordinate, so we can check the core of the velocity vector, calculated as this. So the expression is much more complicated than the Cartesian coordinates. And if we substitute all this velocity component into this expression, we can easily see the expression would be 0. That means the 3D source flow satisfies the condition for rotational flow. And we can also check the Laplace equation given as this, and we can substitute the potential function into this equation. We can easily find it would be 0. Thus, the potential function satisfies the Laplace equation. In here, we can calculate the flow rate through a spheric surface. See this plot. And the flow passed through the surface would be calculated as this. Since on the sphere surface only ur is non-zero, thus we can have this. And we take a stripe, see here, its radius is r prime, calculated r sine theta. So the stripe length would be l prime, equaling to 2 pi r prime. So this part is the velocity component, and this is the stripe length, and this is the width of the stripe. So this part would be ds, the surface of the stripe. And we substitute r prime into the expression. We have this. Then we have the expression as this and this. And we obtain the flow rate passed through the sphere would be a constant q. Now in the last slide, we will apply the Bernoulli's equation for the 3D source flow. The general unsteady Bernoulli's equation for potential flow would be given as this. So the first term on the left-hand side is the unsteady term. Obviously, for 3D source flow, it is steady, thus the first term would disappear. then the Bernoulli's equation for the source flow would be given as this. And P0 is the pressure at the infinite at Z equaling to 0. Then we can calculate the pressure P equaling to this. And we can see P0 here is the reference pressure. We can take it as 0 if we assume the pressure at the infinite at the Z equaling to 0 is 0. And this part, the last term, is the static pressure. It decreases proportionally with Z increase. And this term is the pressure caused by the source flow. So if we set Z equaling to 0, and the pressure difference would be given as this. So the pressure would decrease when approaching to the source. It is inversely proportional to R power of 4. That means when approaching the source, the pressure would change dramatically. This would provide a good property for the pressure field, since in some cases we need the dramatic change in the pressure. So up to here, we can see the elementary potential flow are simple and they are not very exciting. However, as I said, these are the building stones for general potential flows. And in the future, we will see if we combine some of the elementary potential flows, we can see some very beautiful result and mathematics.